domain. I think you are familiar with the GRIP2 format. GRIP2 is the WMO standard format. Last is application models. We are learning the various application models, and the upper is the yellow dot model, and this is the ocean wave models. So global model, the output of the global models is input to this application model. So we should convert the output format. This is the flowchart of post-processing in KMA, and after enthalpy run, and we post-process the data. Usually we produce maybe 200,000 weather charts a day, and it's just stored on our system. We call it COMIS4, and then we convert the data to GRIP, and for the server for DFS, data pocket system, and finally forecast edit this data. So finally the data is services to public domain. Then what is the forecast guidance? And why we make the guidance? Let's just see the why we should know this guidance. This is our definition for data pocket system. Data pocket system means forecast guidance. Let's look at the definition. Its horizontal resolution is 5 kilometers, and we produce from today. We forecast today from today to 2 days, and element is 12 elements, temperature, RH, and P means the probability of probability. So probability of precipitation, and P precipitation types. P is the precipitation amount, rain amount. So, and this is snow amount, sky condition, and wind direction or speed, wave height. So we usually produce the 8 times a day. The interval is just 3 hours. So forecast guidance is the application data of the NWP output, and to support a forecaster and using the statistical method. This image showed the schematic concepts for our DFS system. X-axis means forecast time, and Y-axis issue time. So from today to 2 days, and we generate the guidance at 8 times a day. It shows the times. This is the flowchart of post-processing and not include the weather chart, just only forecast guidance. So real-time model predictions was inputted on the post-processing system, and the data was processed by the trained post-processing method, some correction, and was converted to post-processed guidance. So we will look at this guidance and next slide more detail. Then why we need guidance? And because of limitation of enthalpy. Enthalpy systems have some limitations. So first is physical limitation. And so usually the accuracy of upper level is better than surface. So, but we usually the useful guidance is for the surface. The next is difference of forecast element. Model generate the temperature, RH, wind, etc. But others cannot produce forecast element, the sky condition or rain type. So we generated this element. The last is systematic errors of enthalpy. Some bias according to forecast time or some bias according to train height. And the bias of model itself errors. Usually it comes from physical process. Because of physical process, it comes, this bias comes from physical process. Then what is the role of forecast guidance? Forecast guidance, the role of forecast guidance is the alleviate of the resolution problem. So let's think about the some position, maybe source station. Then but model resolution is 10 kilometers. So we cannot pick the proper position. So we alleviate some this resolution problem. The second is the change the forecast elements using the temperature and RH. We can produce the rain type, rain, snow, sleet, and sky conditions. The last is the alleviate of the geographical and intrinsic error. Some height, real location is, for example, real location is 8 meters, but model height is 500 meters. So because of this difference, there are some adiabatic heating. So it's maybe it's error. So we should alleviate these errors. This is the step of forecast guidance. First, we usually convert a projection method. In the previous slide, I said that we convert equal distance and latitude longitude projection to Lambert component projection. And then selection of the grid. maybe we usually horizontally 5-kilometer grid, and that is calculation of the second variables. But and then we bias correction and blend the guidance output. But maybe these two process, for this process, you don't need this process, because mid-latitude is the remote conformal projection. What is the addition of grids? And for some locations, and the height difference between real and model topography. So we particularly consider the height difference. And horizontally, we consider an land and sea mask. Some area is real location is land, but the model, because of model resolution, it is represent sea mask. So we corrected these errors. And next is the terrain. Topography is the left side image showed model output, and real topo is like this. So after apply to the topographic effect to the original model output, the data was changed like this. So more detailed data. This is the guidance. So another is the calculation of forecast elements. For example, sky condition. Sky conditions, we can calculate 2 elements. Using the 2 elements, we calculate the total cloud amount like this, and maybe addition tree like system. Or we can calculate sky conditions. And another method is an array scheme. Array scheme is the algorithms for the sky condition decision according to the atmospheric condition. So some upper level temperature and upper level the difference temperature and dew point temperature, we can calculate the sky conditions. KMA use the KMA schemes, a little bit modified array schemes. Currently use this scheme. And another example of the rain type. So to calculate the rain types, we use the surface temperature and RH, surface RH. So some conditions and surface temperature and relative humidity, we can, this is snow or this is sleet, this is rain. So And finally, we summarize equation, make a summarized equation, and then apply to our entry model output. So we calculate the sky condition. And the next is bias corrections. And
so, sorry.
Yeah.
Okay.
Yes. What is the difference between sleet and hail?
What is what? One more time. Can you speak one more time?
What is the difference between sleet and hail?
You mean
What is different?
RBA and KMA scheme?
No.
RBA and KMA scheme or?
No.
What?
I just want to ask about what is the difference between sleet and between sleet and hail? What is the difference?
Hail.
Hail. It's
hail and sleet.
Yes.
이게 비투빈에 다 들어가는 거잖아요. 그죠?
그렇지. sleet, hail.
Sleet can include, sleet can have hail, right?
Okay.
Yeah, we just for the convenience for our forecast, we divide by 3 categories. Okay, so but in details in microphysics, and they can make a lot of hydrometeor like hail and graupel and kind of things, but in all those kind of category, we put those things to this sleet category. Okay.
Thank you.
Okay.
Definition of bias is the systematical bias of entropy model or forecast for reference. So it looks like this, and bias equals forecast minus observation. And another meaning, what is the bias correction is the calibration of the model output with respect to the reference data. Reference data means usually the observational data. So the goal of bias correction is to ensure that statistical features of entropy models are coherent with observations. So why we need bias corrections? Because all models are substantial and simplification of the real world, orography or some physics schemes. So all models are not true, not simulate perfect real world. So, but sometimes it's useful, but because of these reasons, so we need the bias correction. There are various methods for bias correction, but we are usually using the variance correction and contour mapping. So we will look at those 2 methods. First, this is the adaptive correction, but the second is scaling, and last is variance correction. Is the variance of observation and variance of models. The relation, use the relations. So the formula is like this. So we usually and this scheme. Next is quantile mapping. We will look at the example of quantile mapping. Maybe next slide. And the transfer function is maybe the regression, very similar to regression method. Operationally, we use the variance correction. So we consider the near past forecast error on forecast data. So this is schematic diagram. So today, here is today. So we calculate the past forecast error for maybe n days means just 60 days, 60. So we calculate the bias, and then we future forecast, for the future forecast, we apply the bias correction to like this. And when we apply to the bias, we using the decaying average weighting method. So the weighting is the strong. 뭐지? 가까운 데가 더 강하게 많이 주는 거?
We give some weighting, considering distance. So right, not a distance. This kind of more closer to a current time. We consider those kind of time, which if the time is very close to a current time, and so we can give the more bigger weighting. Yeah, that kind of strategy.
Thank you. And the quantile mapping is the consider the past PDF probability distribution functions on forecast and observation data. And this is the example of wind speed guidance on Pyeongchang Winter Olympics. So forecast data, models forecast maybe wind speed is like this, and but observations CDF is like this. So we mapped this forecast data to like this. So wind speed is 7 meters per second is mapped to the 3 meters per second. After bias corrections, and there are some improvements. Yellow means decaying average, and green means mean bias correction. So the blue is the raw data. So for the RMS is a little bit, there are a little bit improve. There is an improvement in a little bit. Also, for the precipitations, for CIS score, so a little bit improvement in for each rain amount, cut-off rain amount.
Okay, so It's very sorry for non-smoothing configuration. For still, we could not hear your voice very clearly. So our engineer will come here. So they installed a new speaker for this session. So sorry for that. So we will have 10-minute break, and after that, and we will back here. So okay.
Okay. No
Okay,
problem.
sorry, 10-minute break we will have. Okay, we will back. Can you hear me?
Yes, I
Okay,
hear you.
okay, we will move forward.
We look at the statistical models, for the concept for the statistical models. So look at some example. Minimum temperature forecast for the minimum temperature forecast. And model output is the models forecast the temperature data, but we should consider some other element and sky condition or the location of the site, for example, coastal area. And so so the expected minimum temperature is.
Do you have any question?
Yeah.
No, we will move forward.
Yeah, please go ahead.
Yeah, okay. So we calculated the minimum temperature like this, just some concepts. So the next example of the possibility of precipitation. So we usually the empirical formulas by forecast. So for example, rain amount is lower than 0.5 millimeter. So we define the sky conditions cloudy and define the possibility of precipitations at 10%, or sometimes for the overcast we define the 20%. So if and over the 20 millimeter, and we define the possibility of the precipitations to the 100%. So, this is the concept of the statistical models. So we use the data and training some data. So we get some functions, and then we apply this function to the NWP real-time data. So then we can get the forecast guidance.
Excuse me,
Yeah.
can you back to the previous slide? Yeah. For the empirical formula by a forecaster, does the forecaster decide the formula by their experience or by doing some research? The empirical formula.
어떻게 나왔냐고.
요거.
포캐스트가 뭐 연구를 했는지 경험인지.
Yeah, maybe the forecast studied the research the data. I think research the data as they conclude this empirical formula. So
옛날 데이터가
yeah, all the data.
So it's subjective to the forecaster. I mean, different forecaster have a different empirical formula, or is it a fix?
You are right. And some other forecast and some other empiricals
forecasters investigate all the data from the observation and their forecast. They compared their forecast result compared with the observation from that kind of research, and they make this kind of empirical formula. We have before that, and when we learn the NWP model, and a lot of forecaster has their own kind of some equation to predict some possibility of precipitation, also some fog. We call that kind of things is some regulation for a forecast on some phenomenon kind of thing. So it's similar to this kind of equation. So from that kind of information, we just made that information, that kind of forecast equation from empirical experience of forecasters. We made this kind of equation to our program. You understand?
Okay, thank you, Dr. Andrew.
Okay.
We will look at the PPMs and perfect program methods. This method used only forecast element, only the observation variables to forecast element. So we can get the element relationships, and so we can make some functions. So let's see these diagrams, and for example, maximum temperatures. For the maximum temperatures, we can use the observation and some upper level observations like these elements. So we can get some statistical relationships, region or time, for the region and times. And then we apply to the NWP model output. So then we can get the guidance. So PPMs apply to the PPMs. We assume the model is perfect. So yeah, it's the key point is model is perfect, but in real world, this model is not perfect. So we need to another method, and the model output statistics. And most use between the past NWP output and observation data. So and then apply to the real-time NWP output. The PPM is the assumed model is perfect, but most is considered model is not perfect. So this system's model output and observation data, so get some relations, get some statistical relationships. So look at this diagram. This is for the maximum temperatures, and we can observation, but and other element for the other element we use the entropy element. In the previous slide, we
excuse me, may I ask for discussion?
Okay.
Please, yeah, on the most slide. You said that at least you need 3 years data, or you need some point of observation to do the most statistical model.
Yeah,
So-
yeah, to make equation.
Yeah. For example, if we only have, for example, if we only have 10 point of station, for example, and then I make some equation of MOS, and then how to predict to correct the bias at the other point excluded on the data training. For example, I have 10 stations to create the equation of MOS, and how to correct the other station or the other places. For example, for 11, 12, and so on.
No. First,
You get it?
so you mean you only have data for 10
Station,
point
for
observation,
example.
right?
Yes.
But you want after that from that observation data and your NWP model data, and you can make the model alpha statistics equation, right?
Yes. Yeah.
And then you want to apply that equation to another point.
Yes.
But usually in the model alpha statistics do not apply like those kind of things. But each point observation, if you have observation data, you have unique equation.
Yeah.
One point. Yeah, right.
Okay.
So usually you have to make another
Okay.
new point observation data.
Okay.
You make the new MOS equation for a new observation site.
Okay.
So important part is perfect program method is only you can define some relationship between variables. If your forecast element like visibility, in this example, and the maximum temperature. But if one day, maybe a daytime, you can get the one maximum temperature. For the maximum temperature, you have to consider a lot of another observation field, like 700 hectopascal temperature, 50 hectopascal temperature, or surface condition and relative humidity, wind, the kind of things. From those relationships, you can make some equation, right? But each point has their own one unique equation.
Yes, of course.
Yeah. But problem is, in that case, we just only consider observation data, right? Not a NWP model.
Okay.
If NWP model is perfect, you can use 700 hectopascal temperature data from the NWP, 850 hectopascal temperature data from the NWP. From that information, you can calculate the maximum temperature. If you apply, if your model is perfect means same as observation. So you can apply this kind of perfect probe method from the NWP literature. But NWP has not of uncertainty and from its predictability. Because of that, and so we have to apply this model alpha statistics. From the one in this presentation and 3 years data, and very long period data from the NWP data, and you can make those kind of relationship. You have to make those kind of relationship. Which variable inside the NWP result can make the good maximum temperature forecast? Like those kind of relationship, and so you can make some equation. But one equation is only for one observation site.
Yeah.
Right. So you have to make a lot of. Yeah. Right. So we don't know one location, maybe one location located in some valley area. So there are a lot of different variables to make the good forecast for those points. Some another field, maybe at top of the mountain, maybe Just wind is more good element to predict maximum temperature, but the valley area maybe some radiation, another kind of any other variable is much important than variables in top of the mountain. So because of that, so each observation site need a unique model of statistication.
Okay.
Yeah.
Thank you.
Okay.
And so already answered most need 3 years, maybe at least 3 years data. So, but currently KMA is upgrades entropy models twice
a
year.
year. Twice a year.
Yeah. So we can update. It's hard to upgrade the most system. Yeah.
How long data we need to upgrade our modification? Just 3 months, 6 months?
Just 2
in this time.
Just 2 hours.
2 or 3 months data. Yeah. Well, if you only have
months?
2 or 3 months.
3 months.
Yeah.
But
NWP, not the 3-year data. We cannot get in this time. We cannot get the 3 years data for same model. Yeah, so we our NWP model every year, twice a year, we upgrade our NWP model. So if we have 3 years data, and when we upgrade our NWP system, we have to run before a 3 years period, and then we can get the 3 years data. But we cannot do that. So in this time, and we just only 3 months data to make the modification.
Maybe at least 1 year.
At least 1 year.
Yeah,
1 year. Learn 1 year, more than 1 year, and from the data, and we can make the model output statistics equation. Do you have any kind of post-processing like this kind of model output statistics, or some perfect prog, or some multiple regression kind of thing? Do you have?
I think we don't have now, but next we try to do this.
Okay.
Maybe Baita can explain how the post processing at the your center, Baita.
Yeah, Pak. In public weather services center, we usually use NWP data from many parameter to make us a guidance. So we produce daily guidance for forecaster all over Indonesia, for especially in a coordinator station. So we have the same perception, but it analyzed by the senior forecaster manually. So this procedure must be done before 11 o'clock, and then the guidance will be disseminated to the forecaster in all province in Indonesia, and we do it manually, Pak Urip.
Okay.
So, but there is no kind of some regular program, right? In a forecaster, and manually make the guidance, right, from the result of NWP.
Sorry, can you repeat, Dr. Ang?
So, do you have a kind of some computer program to make the guidance?
No.
Yeah, right. Forecaster and manually.
Yeah.
Just the guidance from the display and kind of thing.
Yes, the guidance consists of the important phenomena like a tropical cyclone, trough, and then IPTZ, and then the area of the area, the heavy precipitation, something like that, convection, and then convergence for next 3 days.
Okay. So but when we start this kind of forecast guidance, and we also same as you, same as your way. So forecaster manually made this kind of guidance at that time, and but in their subjective method to make some guidance. So we made some kind of empirical formula. Yeah. So after that, and we applied this kind of equation.
Yeah, this is very interesting for us to create the forecast guidance with the empirical model and also statistic. Yeah, that's very important. So
Right.
Yeah, maybe later if we have a long-term and WP archive, so we can do with the statistical model.
Okay.
Yeah. Thank you very much. This is very interesting. Yeah.
Okay.
Dr. An, can I ask something?
Okay, go ahead.
Do you separate the equation based on the season?
So okay, let me check. 계절마다 따로 식을 두고 있나요?
Yes.
Each season. Yeah. We have a equation for each season.
This is example of the coefficient.
January and
both.
July. Yeah, right. Okay. January is winter time, and the upper part in presentation of winter time, and the lower part is summertime. Same location, but different equation. Coefficient. Okay.
Yeah. Skip to this slide. And another method is the linear regression. So I think you know the linear regression. Linear regressions show the linear is simple and reasonable, and easy to make and handle mass data. But it's assumed normal distribution. So sometimes it's have not good performance. But most ppm is the example of the linear regression. So when we apply to the this methods on our entropy data, we get better than low entropy data. So this is example of the improvement of the performance. So, this is temperature and RH, and this is possibility of precipitation. Next is the logistic regulation, but currently we cannot use this method, so I will skip this model. The next is neural network. Neural network is the machine learning based system. So it can find the unknown relationships maybe automatically. So, but sometimes it has some overfitting problems. So, but this problem is just initial 초기
초기 데이터
초기
뭐 때문에?
뉴럴 네트워크.
네, 근데 초기 뭐 때문에? 초기
이거
트레이닝 데이터?
initial neural network has just one hidden layer. So because of this, it sometimes repeating problem. So at first we considered this neural network just only having just only one hidden layer, but the result was not good. So currently we use the deep neural network.
Ray, right? First,
Yeah,
we when we apply this method, is original neural network,
maybe
not a deep learning. Original neural network has one hidden layer, but in
no.
recent AI method, deep learning has several deep layer. So we want to apply those methods to improve this neural network.
Look at I think you are interested in this method. We are using the LSTM, the long short-term memory network. It's a deep neural network. So we apply to this method to the temperature forecast. So a little bit, we had a little bit improvements. So yeah, I think it's a good method for the forecast guidance. If you are consider some method, I recommend this method.
LSTM, right?
Yeah, LSTM
method is much better.
So we are for the sky condition or precipitate rain types, we usually the decision tree method. So it's a random forest. I think random forest is the ensemble of the decision tree. So, but it has a limitation in making large number of models. So because of it's weak to big data. This is the result of the random forest. So RF means random forest. We apply to the ECM data. So you got some improvements and some range of temperature or all range for all range, we got an improvement. Next is the ensemble MOS systems. This is very similar to previous MOS systems, but just this system uses the ensemble model output. So the predictant and predictors, elementals combined with the statistical functions. So, and then the real-time ensemble data was converted to the ensemble guidance. So forecasters these data for medium range forecast. KMA is run the ensemble members 24. this is the result of the ensemble most systems. So blue is RMSE and red is spread and green is bias. So all scores is improvement has the improved. So last method is blending. Blending is we run various methods for the model outputs. Sometimes ppm, sometimes MOS. So each model is some improvement, better than the original model data. But if we blending each models is like ensemble systems, we thought we will have more improvement if we blending each statistical model output. So it's the concept of the blending. So it's, for example, the model A, maybe in our case, Kim, or B is C is ensemble ECM dwarf models. So we blend each post-processing result, then we can get the best guidance. Do you understand this concept?
Can you understand? So we have a lot of forecast guidance method to make the good forecast guidance. So final blending method is to combine all forecast result from the forecast guidance. We can make the best result.
Yeah.
To support the good forecast. Okay.
Sorry, Dr. An. Theoretically, we understand what you presented about the post-processing method. But my question is, do you use all this post-processing method in your daily operations? And whether forecasters are required to see the result of the post-processing and making forecasts? Because I see that there are many post-processing methods you have, and do the forecasters are required to see all the result of the post-processing?
No. So they want to see the best result. Because of that, and we make this kind of a blending forecast result and make the good forecast guidance. We applied a lot of technique like traditional MOS and AI-based and a lot of forecast guidance. We can combine all those kind of results. From those kind of combination, we can make the best result. Yeah. From this kind of a blending technique, we can make the best result, and we can give the only one forecast of guidance to forecaster. That is our strategy. Each method to make the forecast guidance is not perfect. Sometimes, but all the time, we apply the PPM, MOS, and the AI-based method. But
how to select?
How to select is
the selection have done daily, or there are some SOP to select the best method you use.
Yeah, right. It comes from the error-based weighting, right? So how wrong? But he want to know how wrong, and one day verification result or
60 days.
60 days. 60 days.
Oh.
3 months. No, 2 months. 2 months from the verification data for 2 months. From that information, we can make the weighting for each model.
Oh, okay.
Yeah, okay?
Okay.
Yeah,
Me, Dr. An.
6 days.
Yeah, okay. Go ahead.
If the forecaster feel doesn't satisfy with the guidance, may the forecaster doing doing expertise to the guidance.
So if they do not satisfy this guidance, so last word I couldn't hear.
Yeah, may they make a modification or
Right. Yeah, we have some kind of we have some kind of editor. We call the forecasters editor. So some kind of data map from this forecast result, and they can modify with their fan, and so it'll increase temperature, tomorrow temperature, or kind of things. So from those kind of forecasters editor system, so forecaster can modify all this result from the forecast guidance. Okay.
Okay, thank you.
Okay.
And this is the concept of the error-based weighting. So we graduate to model with small error, a small weight to the models with large error. So yeah, with using this method, we blend each models. So this like this weighting is this show the weighting for each model. The best means red is best, and it means the blending the result. So and whenever error or and yeah, error is improved and for the best. So this is it's interesting. The forecasters blue is forecast. So best is the better than forecaster. So but the forecast manually and modify our guidance to make a decision. Some severe weather for the severe weather. So generally, we think that our best guidance is better than forecast, but and some situations is forecaster decision is very important. And this image showed our schedules for the produced guidance. Usually we produce the guidance 3 times, and for each 3 times each for example, and UTC, we produced guidance 3 times. And at first we use the data at these times, available at these times, and then after running ensemble systems, we upgrade our systems, and then after getting the ECMWF data, forecast data, we generate our guidance. So maybe 3 times.
Now from 3 steps, and we update our guidance result first, and from original numerical weather prediction result, and we can make some initial forecast guidance, and then if we have a result from the ensemble model, and we can upgrade the result, and the last and finally, if we get the ECMWF result, and we make the final forecast guide result. Okay.
The last year we this is show the example of blending for the rain types. And we use to decide the rain types. We use rain type, rain yes or no. We decide to rain yes or no. We blending the available models and KIM, UM, and ECMWF. So if 2 or more models have rain, some same area, rain yes. This is the schematic diagram of the concepts. And then for the rain and snow amounts, if for rain yes, and the amount is the mean of each rain snow amount. So look at this area, and 0.5 is 2 models have 0.5 is the final result is the mean is 0.5. So this is the current status of forecast guidance in KMA. So short range forecast, we around 3-hour forecast and 3-hour interval forecast and 1-hour interval forecast. And for each element, for example, temperatures, we use the best is the blending. Also for RH, the best is blending. But for the wind speed, the best is the ppm data from the global model. So sky condition is the best is the blending of each ppm output. So for the medium range forecast, we just produce the guidance, temperature and sky condition and rain type and probability of precipitation. So for the medium range, we use the ensemble. Using the ensemble systems, we generate the best guidance. For the service, you can see the weather chart on KMA homepage, and I think you visited this webpage. So you can see the weather chart. And this is our internal intranet web page product guidance. So this is the element of the guidance. So this is the just only for the templates.
Sorry, may I ask this slide, please? This internet web page of guidance for short term. This graphic representing the point of station or representing the grid?
Grid data?
Grid data.
No. Just guidance data. Blended
final result from the forecast guidance. I already explained combination of all forecast guidance result. From that kind of strategy, we can get the final guidance.
Oh.
Yeah, this internal web page.
Yeah. You mean that there is some identity for 7108? This is the station number?
7018? Yeah, right. 47. Yeah, right. 108. Yeah, right. 47 number and 108. Right.
This is the station ID?
Yeah, right. In Seoul City.
Okay, thank you. Yeah.
Okay.
So we currently produce station-based guidance and grid-based guidance. So this is the example of the grid data. And yes, so this shows the ensemble guidance. And this is our monitoring systems, the storage usage and process status. And so other, maybe you can show the ppm or each model for each model, GDAPS or EPSG, ECM models, and EC ensembles. So we monitor this system. And the last is the future of post-processing. Already I showed this slide, but most PPMs are usually linear regression, but real-world data is not linear, so non-linear. So it's I think AI, maybe the deep learning is the good method to solve the non-linear problems. So last year we applied this LSTM method to our temporal guidance on based model output. So we are, I think we had a good result. Yeah. So we plan to another element. We plan to apply this method to another element, relative humidity and wind speed. Yeah. And considering this year we considered another deep neural network method, and maybe its starting point is the CNN method. Yeah. So This image shows the red dot is the over
2 degrees
2
Celsius.
degrees Celsius. So, but after LSTM method, we had just maybe 10 red dots. So, yeah, so we think LSTM is very good method.
그렇지. 쟤네들 점심시간 다 돼가는데. 오케이. Okay, yeah, that's it. Do you have any question?
Yes, I have.
Okay, go ahead.
My question is for the data collection for the MOS. So as you mentioned that we need at least 3 years data to build the models.
Yeah.
So what is your reason to use at least 3 years data? So because in my division we will apply the model, but because we have only very limited data, we only have 2 years data. So,
Okay.
but the data is very, very large. As you know that we have 2 years data for the output of the model. We use hourly data. So for the capacities is very big, but only for 2 years data. So may I ask your reason for that? Thank you.
So we already explained this kind of things, but we in this time we just only for a 1 year data, right? More than 1 year.
Minimum
1 year data, but then yeah, I know there are a lot of problems to extract the data from the very long period result. So can you say something? 큰 많은 데이터를 갖고 뽑고 뭐 이런 데 문제가 없는지 뭐 이런.
I think we don't have any problems for the data processing, but to get data for the long period, we cannot run the entropy model. We cannot run the entropy models because of the HPC resource problem. So data processing is, I think, not problem at KMA, but model learning is the big problem to get maybe 3 years data for most guidance, I think.
So lastly, we decrease those periods, right? Decrease those periods to 1 year, more than 1 year.
So maybe AI method to overcome this handicap.
Yeah. So AI-based method can handle this kind of problem, this kind of issue for a longer time. AI can apply the very short period data and can make the good result. But sometimes it is, I don't know. So, but then we from some example from the LSTM or kind of some another example, and we can get the good result from the very short period data. Okay.
Okay, thank you.
Okay. Do you have any question?
Yeah, may I give some comment? Thank you for your presentation, Mr. Chang Yan. You have some example, especially for the maximum temperature or minimum temperature or something connection with temperature. But in Indonesia, we focus on the rainfall forecast because you know that the variation of the temperature is very low comparing with the rainfall. So it is our challenge to make some correction for the rainfall forecast. What do you mean? What do you suggestion?
강수량은 어떻게 해야 될지 제안을 해달라는데 우리는
강수량.
강수량을 가이던스를 만들고 싶은데
강수량.
우리도 그냥 probability of 하나요? precipitation?
강수량 자체는 일단 지금 현재 이제 단기 같은 경우에는 단일 모델 결과를 사용해서 그걸 이제 여기서 지금 보는 것처럼 민을 하지 민.
한 멤버밖에 없는데 only one member.
UM, 김, 이씨.
아하.
and 그다음에 12시간 전 데이터. 그러니까 방식이 여러 가지인데 내가 설명하고 기본적으로 이제 UM, 김, 이씨 쓸 수가 있고 지금 이제 하고 있는 방식이 이제 12시간 이전 데이터, UM, 김에 대한 이전 데이터도 가지고 와서 이제 여러 멤버들을 이제.
Okay, so we in this time we applied some kind of blending method from the several model, and for example, we have a prediction from the unified model and also ECMWF, also our Kim model. From three kind of rainfall result, but in a very much different, right? Different field. So we can make some mean field from three model. This kind of astrology, like ensemble mean, and we can make the more reliable forecast. That is current our method. Also, yeah, where I did this chart, and for in this time we apply the previous forecast from the Kim, UM, and ECMWF, and the current forecast, but in the valid time is same. We got a lot of model result. From that result, we can make some more combination, more best result. It is kind of some concept from the ensemble mean.
Okay.
Okay.
Yeah. Thank you.
Okay. Let us finish this morning session, and so after lunchtime and 1 p.m. and we will meet. Okay.
Okay. Thank you.
Yeah. Okay. Hi, hello. I'm back.
Hello, sir.
Yeah, have you good lunch?
Yeah. We did.
Okay, so we will move to final session and 2 hour for the Wolf DA. So I'll introduce a new lecturer. He's working on data simulation. Also, he write paper, the Wolf DA paper. And, so he will introduce all this observation pre-processing and also Wolf DA. Also, if you want to improve the result from the Wolf DA, and he can explain the short from his short experience. So I'll introduce my colleague and Mr. Chewon. So he will give the lecture, give his talk.
Hello.
Can you hear me? Hear us?
Yes.
Okay.
Hello, my name is Won Choi from KMA Numerical Modeling Center. Can you hear me? 안 들리는 것 같은데요?
Very clear.
Yeah. Okay. Hello. Did you enjoy your lunch? I have been working for 24 hours since yesterday, so I ask for your understanding. My presentation is about pre-processing of observation data during OpenDA simulation system. Data simulation is a process of reducing the errors of NWP model by adding observations to the initial condition of NWP. Therefore, in order to data simulation, pre-processing for observational data is needed. Okay. The order of my presentation today is as follows: introduce OpenDA system, observation format, and observation pre-processing. Data simulation in NWP aims to optically blend information from observation and model to produce an accurate and physically consistent estimate of the initial state of the atmosphere and of the
window block. It means okay. Okay, so how about this time? Is it okay? Okay. Yeah, right. Okay.
이 화면
안 몰리는구나.
Okay. 어디까지 있더라? 네. Data simulation has two main goals. First, make the best estimate of the initial state of the atmosphere, land, ocean system out of all available information. Second, quantify the uncertainty of our estimate of the initial state. The initial data of the numerical model used in data simulation contain forecast errors, and observation data contains observation errors. It's a data simulation that produces an analysis field with relatively small errors using data simulation error. Using data using data contains error, supercomputer, and data simulation method. The flow chart for data simulation system of open model developed by ENCA. ENCA is as follows. WPS is a WPS is a pre-processing process that produce initial and boundary data for numerical weather prediction model. When data simulation are carried out, the initial data change due to the influence of the observation data, and the boundary data need to be modified accordingly. The part that performs this process is updated with C. Among OFDA system, pre-processing of observations is performed in OBS proxy. Please refer to the OFDA user guide chapter 6 for more information. Before I explain the pre-processing of observation data, I will tell you about the process of installing the OFDA system. To compile the OFDA code, the mandatory library is the NashDev library. You should set an environment variable NashDev to point the directory where your NashDev library is installed. Some external libraries are included in the tar file. If satellite radiance data are to be used, a radiative transfer model is required. The CRTM version 2.3.0 source code is included the tar file, and is compiled automatically when compile the OFDA system. If you wish to use RTTop, download and install the RTTop version 12 library before compile OFDA system.
Okay, so I have one question. Do you use satellite data for your OFDA system?
No, not yet.
Not yet.
Yeah, we plan to implement it maybe in next 1 or 2 months.
1 or 2 months. But then I heard, I saw some experimental result from the satellite simulation in OFDA.
Yeah.
OFDA, right?
There's some a student from the BMKG. He working on the satellite simulation using Himawari from Japan.
So what is planned when you apply the satellite data simulation, and which radiative transfer model you use, CRTM or RTTop?
We use the default one, the CRTM.
CRTM. Okay, thank you.
Welcome, sir.
Assuming all required libraries are available and the OFDA source code is ready, you can start to build OFDA using the following step. Each option combined an operating system, a compiler type, and a parallelism option. The available parallelism option are single processor and shared memory process parallels and distributed memory parallels and distribute memory with shared memory parallels. However, SM bar and SM plus DM options are not support as of OpenDA version 4.1. So we don't recommend selecting any of these options. In the case of KMA, the parallelization and compiler options were installed using DM4 and Intel compiler. After running the configuration script and choosing a compilation options, configure point WOP file will be created. Because of the variety of ways that a computer can be configured. If the OpenDA build ultimately fails, there is a there is a chance that minor modification to the configure point of file may be needed. Successful compilation is produced 44 execute tables, 43 of which are in the bar/build directory and linked it the bar/da directory. Our OBX proxy point exe find the bar/OBS proxy /SH directory. The OBS proxy program reads observation in literal format. Literal formats are text-based format in use since the MM5 eras. The performance of OBS proxy is to first remove observation outside the specified temporal and spatial domain. Second, reorder and merge duplicate data report. Third, retrieve pressure or height based on observed information using the hydrostatic assumption. Also, check multi-level observations for vertical consistency and super-adiabatic conditions. To make the best use of the OpenDA program, it is important for user to understand the literal format. The report can be divided into the three main parts. For example, a surface station report including observations of temperature, pressure, humidity, and winds. Upper station sounding report with temperature, humidity, and wind observations at many height or pressure level. First, the report header record is a 600 character long record that contains certain contains information about the station and the report as a whole. Shared items in the table are unused. Therefore, the KMA adds information such as the number of observation data to unused items. And second, the data record contains the observations of pressure, height, dew point, temperature, wind speed, and wind direction. For report type that have multi-levels, each pressure or height level has its own data record. For report type that have a single level, the report will be a single data record. So the end data record is simply a data record with pressure and height field both set to -777. After all the data records, then the end data record and report record must appear. The end report record is simply 3 integers, which really are not all that important.
So I have one question. You already have a decoding program to make this linear format for your WRF-DA, right?
Yeah.
But when we start this lecture and you asked some decoding of observation data for a WRF model. So which kind of in this part, he explained just the format of literal format. Then, do you want any more about this format, or so? Do you need more explanation for another decoding?
I don't know for others, but for me, we already implemented. Yeah, we already make it with our own code.
Oh yeah, all your code. And so which observation data and your radio zone?
Yeah,
data?
radio zone, radar,
radar,
AWS, kind of data. Yeah.
Okay, great. We will move forward.
Yeah, next is part of our main program, and name is used by the KMA to process observation data. Left is a program name list, and right main program. Selecting the date, time, program path, and observations to use in the name list change. Selecting the date, time, program path, and observations to use in the name list change the various type of observation to literal format. I will provide the source code for the data convert program as an attachment.
Okay, thank you. It might be very useful for us.
Okay. Yeah.
Okay. Yeah. Next, this is the AWS sample observation data of the KMA. The AWS observations consist of time, station ID, and temperature, wind information, and sorry. AWS observation consistency of time and station ID and temperature and wind information and precipitation, humidity and sea level point and mean sea level pressure. Next subroutine programs convert the sample AWS data shown above the format using the Fortran program. In the subroutine program, the data input part is green. The variable calculation is blue, and the data output is red box. The format of the data output used the literal format mentioned earlier. The following is the temp, sounding, or radio zone sample observation data of the KMA. The temp observation consists of the time and station ID, pressure, geopotential height, temperature, dew point, wind information. So the location information for the observation point was made and used separately. And next subroutine programs convert the sample temp data shown above the format using the Fortran program. In the subroutine program, the data input part is green, and the data output is a red box. The following is sample data in literal format created using surface observation data and Fortran program. The first line contains information about the location and time of observation point and the type of observation data, latitude, longitude, and station ID, station height, data, and data type. False is a single level, and true is a multiple level data. Second line contains information about the pressure and temperature, humidity, and wind at the observation point. Because it is surface observation data, the data record is one line at the out data record and the report record are entered after the data record. The following is sample data in literal format created using sounding observation data and Fortran program. The first line consists of the same information at the above surface observation data. But however, sounding observations you need to change is underbar sound to true. Surface data is first. In this case of the sounding observation data, the data record consists of multiple lines because it's observed multiple level vertically. Upper observation typically use data for standard pressure level, but you can use different intervals. Next, sample name list of the OBS program. The name list contains information about the observation file path, observation error, time information, thinning options, domain, and so on. Observation error was provided by ENCA for a detailed description of OBS proxy name list. Please refer to WRF User Guide Chapter 6. The following is a part of the log file output. When OBS proxy is executed, if you look at the contents of the log file, information about the number of observation data, the number of empty number of observation data, and the number of empty observations, the number of observation out of domain is printed. Also, the number of observation removed through the basic quality control process is printed. This part is a number of observation, and second box is a quality control information of quality control. Finally, the number of data according to the observation type is printed. In the future, it would be effective to check the observations used in the data simulation using this information. SYNOP report number of SYNOP data 773, and then sounding the number of sounding, so 120, and satellite data is satellite data, number of satellite data and 30,000, and so on. Yeah.
Excuse me.
Yep.
Can I ask you something? For the sounding report, did you use all of the pressure level from the data, or just use the significant level of the data? You know that the sounding has the raw data input, right? That has many level instead of significant that only few level. So for the assimilation technique, did you use the raw data of the synop data, or just the significant level pressure?
Just sorry. I ask my boss, and then I will.
Okay, sure. And for the KSCAT, is it the QuickSCAT data?
Yeah, QuickSCAT data.
QuickSCAT.
Right.
No. QuickSCAT. QuickSCAT is satellite data.
It's a WIN, right?
Yeah, wind radar. Yeah, satellite derived wind.
Okay.
In the surface wind, right?
Yeah.
And also for the first question about the sign-off data, did you use the raw level pressure or only the significant level pressure data for the sign-off?
Sign-off?
The sounding data.
Sounding data.
Yeah.
So, report to you. You want to know
How many level did you
pressure,
use?
Right?
Yeah, how many level did you use? Is it using the raw data or the significant level pressure?
Okay, wait. 850, 700, 500 이런 시그니피컨트 레벨 데이터나 쓰는지 아니면 로 데이터 쫙 많은 거 있잖아.
GTS로 들어오는 거는 프레셔 레벨, 스탠다드 프레셔 레벨만 쓰고 KMA는 로 레벨 잘 쓰습니다.
지금 이거는 okay, yeah. So usually if we use GTS line and we use data in a significant level, but in our KMA observation data over Korea Peninsula, and we can get the raw data, right?
Yeah.
You understand? Only for the Korea Peninsula, our own KMA observation data, and we can use those data with raw data as a raw data, the many level. But in another, maybe China and Mongolia, Far East Asia, another countries' data, and we use only significant level data.
Okay. So in our case, if we have the raw data for our regional model, so it's better to use our raw data instead of the significant level, right?
Yeah, right. Only for the Korea Peninsula, our own KMA data, use those zone data as a raw data with raw data. We can get the raw data from our FTP. But in another and the GTS site, another countries like China and Mongol, and we just only use that data in a significant level.
So it is important to have all of the raw data if it is there. I mean,
right.
If it is, you have access for the data.
Yeah,
if
it
it
is
is
possible.
not, you just use the significant level. Okay.
Yeah, right. If possible, and if we can use raw data, I think it's better for data assimilation. But then we have some limitation to collect all those raw data, right?
Yeah.
Okay.
Okay, I get your point. Thank you.
Next slide. This is about pre-processing of radar observation data. Radar observations are effective in monitoring rapidly developing hazard weather conditions. To use radar observation for data assimilation, coordinate transformation system is required because radar observers based on sphere coordinate system and numerical model is based on the Cartesian coordinate system. The option newly available in version 4.2 direct simulated radar reflectivity with a new observation operator and this tangent linear model and adjoint model taking into account snow and cloud path. And radar non-echo assimilation options can be important radar simulation techniques. Normally, you cannot remove precipitation from your analysis without using the retrieved water vapor option. This program transforms the coordinate system during the pre-processing of radar observation data. It will be useful as a reference when making a program to process radar observation data in the future. After the coordinate system transformation, the data of the point nearest to the model grid is used for data simulation. Radar observation data is input to WRF-DA system in ASCII format, like convergence observation data. Conventional observation data. However, radar observations are different from the format of conventional observations. Please note that this program output radar in ASCII format. Next, this is the radar sample input data converted to ASCII format. And the first line of input data contains the number of radar. The second line contains the location and time information of the radar station. 어디까지인지 까먹어가지고.
The second line contains the location and time information of the radar station.
네. And observation data about the point. In the case of the KMA, both radar radial velocity and reflectivity data are used for data simulation.
Okay, at this point, I have one question. Do you using your radar data for your FDA?
Sorry, can you say it again?
Radar data simulation for your FDA from your radar data.
Yeah, we had.
33 radar all use?
Yeah, it's about 32, 33, yeah, something.
30 to 33. So is those methods to decode radar data is like this kind of method to change it to a literal format, or?
Maybe Mr. Donali can answer that, or Mr. Jaka, because he's the one who created the code.
Right. I know. He did work for radar data simulation, right?
Yeah, but the point I think is the same. We are scanning the velocity and the reflexivity data for each layer of the data. Oh, sorry, of the radar.
Right. Okay. Thank you. We will move more.
Currently, the KMA in developing a next generation regional numerical model focusing on the East Asia region. Their figure show the observation data used for data simulation in the area of the regional numerical model. Currently, we want to improve the forecast performance of regional numerical model using various observation data, such as surface, aircraft, temp, radar, satellite, and so on. We plan to use more satellite data in the future. Next, I would like to tell you how to assimilate conventional data and radar data at the same time. In the WRF data assimilation system, conventional data is entered as OB point ASCII, and radar data is entered as OB point radar. In order to assimilate the radar observation data, you need to edit WRF bar 4 and WRF bar 7 and radar data record, radar DA record in the WRF bar name list. This record the part that select whether and how to execute radar data simulation. Please refer to the WRF user guide for more information. When the selecting relative to radar data simulation is complete, place the two data in same directory and execute the WRF-DA main program. To run WRF-3D bar, the following the step below and this box. Thank you for your attention. This question?
Do you have any question for observation pre-processing in the WRF-DA? Do you have?
Yes, sir. I have one question about the QuickSCAT satellite data.
QuickSCAT satellite data.
So, is it the same method you use for the pre-buffer format? I mean, I know that the QuickSCAT output is in NC format, right?
That's the format, right?
So, do you
QuickSCAT data
convert it into
buffer format?
Oh, it's also buffer format?
Yeah, right.
Okay, so you can use it directly into the data
WRF
data assimilation. Is that you do not need to convert it, right?
Yeah, right.
Okay.
So did you usually collect QuickSCAT data?
No, we are not using it for now. I think we also interesting to use it the QuickSCAT data as our data assimilation input.
Okay. 그게도 이상이잖아. Okay. So any question? If there is no question, and we will have a 10-minute break after that, and so current minute is 47, and we will meet for 57. Okay, we will be back.
Okay.
Okay, see you.
Okay, thank you.
Thank you, Mr. Choi.
뭐 나와 있지? 이걸로 적어야 돼. 이걸로. Okay, we are back. He will show the program from our supercomputer. So give a second. He wanna increase the character size. So can you see the screen?
Yeah, but it's not in the presentation mode.
Yeah, but in I would like to. Yeah, it's not a presentation. It's from our background. Can you see this screen?
I show the presentation only.
Presentation only. Okay.
Yeah.
Okay. How about in this time? Could you see the?
I didn't see anything. I just see the screen behind you, the black screen.
Right. Yeah. Right. That screen is our supercomputer screen. So
okay.
이쪽으로 돌아 앉는데 그렇게 앉지 말고 이쪽으로 그냥 이쪽으로 돌아 앉아서 약간 돌아 앉아가지고. Okay. So can you see the this is can you see the character too small or enough to see?
No, it's too small, sorry.
Too small. Okay, much bigger. And can you how about
you cannot put it into the sharing screen because I think it's impossible for us to see that screen.
All right. Is it not impossible? How about this?
No, it's still.
So I heard they don't have any function to share this screen.
Oh, okay.
To you. So he wanna show you his program.
Okay, maybe let me try to increase the view.
Screen.
Yeah. Yes, I can see it now.
All right.
Let me tell.
How about that?
Yang lain mungkin bisa di view-nya itu jadi speaker, jadi bisa kelihatan.
Can you see this black screen?
Yes, I can see it now. Yes, clearly.
All right. Great. This is any other people, and the other people can see this screen.
Sorry for interrupt, but for me, if someone else like Pak Wido speak, then the screen is changed to his window, and your screen is not appear in the main Zoom.
Dipin aja Ida, dipin screennya dia dipin, jadi punya dia aja yang muncul di tempat kita.
Gimana caranya ngepinnya?
Di pojok kanan itu ada yang titik tiga itu.
Speaker view.
Iya, just choose the speaker view.
Recording in progress.
Okay, bigger. Can you see?
Yeah, I think it's better if the background of the screen is black instead of white.
Black. Okay. You thought this background white background is much better to see, but so black is much better, right? Much better. Okay.
Yes, it's much better.
Right. And this is our supercomputer, but in that exactly is not a supercomputer. It means this name is NGate. NGate is another Linux cluster, not a supercomputer. We cannot directly connect it to the supercomputer. We can connect to gate server, and we call that kind of server is pre and post processing server. It means our supercomputer structure is a little complicated. In the original, our supercomputer in the middle part, located in the middle part in some very important part, and the block or any other connection. Only pre-processing Linux cluster server can connect to the our supercomputer, but just only using a job scheduler like PBS. Just we can throw the job to a supercomputer. We cannot direct connect it to the supercomputer. This NGate means is just the pre-processing server. So he will show the process for the background data covariance. I already mentioned about important part to improve your data simulation and your model. As one is write the background error matrix for your own model, and the second is variational bias correction. Bias correction is simple work, and so if you have some bias in your observation data, you have to eliminate. Also, when you compare model background data with your observation data, if there is some bias, you have to correct. Also, some satellite data in a warp DA provide function to eliminate those bias from Bar-Bishi technique in the lame list. In that case, that kind of bias information, you need to put the bias information in your satellite data, but in most satellite data automatically has their own bias data in their everyday their observation. So bias correction is not a problem, but in background error covariance, so he will show the process, but it is originated by NMC method. So he will explain. He will show the first step in background error covariance, which program is. So I think this background error covariance matrix program is when you install your warp DA program. So in this warp DA program, and you can find. And Gen B. Can you see Gen B directory, right?
Yes.
Yeah, bar script and Gen B directory. And so in this directory, you can find this kind of cone shell script. So, okay. So from this cone shell script, so you can explain. So first, which one we should do? Which one we have to do? So first thing is in this script, in which kind of part we have to modify? 설명 어디서부터 바꿔야 되지? 설명 그냥 해도 되고 하려면. 그러면 뭐 한국말로 하면 내가 얘기해 줄게. 뭐 해야 되지 첫 번째? You have to put your directory.
첫 번째로는 최소 한 달 정도 프로세스 모델 결과가.
Okay, you need at least 1 month NWP result to calculate this background error covariance. At least 1 month. If you can collect more, and it's better. Also, in this concept for background error covariance matrix, you need to integrate your model up to 24 hours, right? And the NMC method, and usually 12 hours, we can consider it as true. And the 24 hour, forecast is NWP prediction. So you need to calculate the difference between a 12-hour forecast and the 24-hour forecast. So before this script, you need to prepare and at least 1 month NWP result. Then in this script, and you have to put this directory wolf by dir, and so external and so environment, you have to put this, and also CB option is control option is this is 5, right? What means 5?
5번이 이제 여기 보면 디폴트 윈드 컨트롤 베리어블 그 윈드를 저기 파이랑 사이 바꿔가지고
Okay.
그냥 기본적인 이고요.
This is default option for your background error covariance, but in the background error covariance matrix, and do not use any other normal variable because there is some dependency between variables. So because of that, and they choose the control variable. It's kind of independent variable. So psi chi from the wind variable, and you can calculate psi chi variables. And then, so what is that? Bin type 5, and so
how data is being
you have to put the bin type 5. Yeah, to average of all horizontal point, not only several point, all point, and also next. This is valid time means this is at least if you have 1 month's forecast, and you can put the start date and end date.
여기서 스타트 레이트는 모델 시작 시간이 아니라 첫 번째 퍼터베이션에 그러니까 두 개의 모델이 그래서 첫 번째로 이제 섭동을 이루는 예측 시간이 들어가는 겁니다.
What mean? 뭐지?
그러니까 이게 7월 1일 00시에서 24시간 폴캐스트 한 거하고 7월 1일 12시에서 12시간 폴캐스트 한 게 첫 번째로 만나는 24시간.
Okay, yeah. This start date means is I already explained this background error covariance matrix need the difference between a 12-hour forecast and the 24-hour forecast. Start date means not the initial time for your forecast result. It's the first matching time between a 12-hour forecast and the 24-hour forecast. It means maybe if you integrated from the July 1st, 12 UTC. So if so, and you can have the 12-hour forecast data for this hour. Also 24-hour data. Maybe if you integrated, your initial time is July 1st, 00 UTC. Also July 1st, 12 UTC. Two initial data, NWP result from the two initial data, you can find the first matching date, like July 2nd, 00 UTC. You understand? You have to put that date in the start date. And the date is the final matching date, right? Okay, yeah, so number of level is mono level in the 39, in our case in 39. And the background error covariance method is NMC. We use NMC method.
넘버 레벨은 폴캐스트 모델의 버티컬 레벨 -1.
Right, so this is not a C grid, right? Not Araga C grid. So just only calculate a mass point. Because of that, and E per -1 point is 39. It's how many level you have?
33.
33, it means you have to put the 32, right?
Yeah.
Okay.
Excuse me, doctor.
Yeah.
So for the output of the WRF, is it split file or one bigger file, one big file?
Slice 파일로 줘야 돼, one big 파일로 줘야 돼. 내가 뭘로 적어놨지? 슬라이스 파일로
슬라이스 파일.
Yeah, sliced file, not one big file.
So it's split every 12 hour?
Yeah, right. Every 12 hour. Maybe if you integrate for only one case, 00, and the 12-hour forecast, 24-hour forecast, three file.
Mm-hmm.
You understand?
Yes.
So just one case, 3 file, at least in 30 days. And you have, if you have just only one time a day, so just 90 file, right?
So what if we running the model 4 times a day?
Right.
So is it the GNB file will be like for the 00, it's 12, 00, 12, and 24 hours. And then for the 06, it's 06 and plus 12 and
Right.
plus 24. Okay.
But then usually we use all data like 4 times a day. You have 00 UTC forecast and 06 and 12 and 24 UTC forecast 4 times a day. But it means this background error means NWP error, not only for 00 UTC's error.
Okay, so it's for total day,
Right.
1 day. Okay. So if we plan to run it twice a day, so then we have to use the 00 and 12 UTC background error.
Right.
If we want to increase our number of forecasting UTC, so we have to make it a new one.
Right.
Okay.
But then, it's better. But then sometimes you have to carefully choose. Sometimes, but then, but very different from the initial time of NWP. So because of that, you have to carefully choose. If you run the 8 times a day, so you have to calculate one more time. I think I recommend those kind of things. But in sometimes you have a lot of limitation and maybe a storage and kind of some computer resource and at least 1 month's data. And also if you don't have any other times in a day, so just at least 2 times a day, 00 UTC and 12 UTC is very important. It's kind of daytime and nighttime, and starting point is morning and starting point is nighttime, and those kind of things is very much related to our diurnal cycle. Because of that, and I recommend this 4 times is much better. But if you don't have any computing resource, just only 2 times a day. But then carefully apply those background data covariance to your work DA. But if you have bad result in the right thing is to make your own times result, right? Okay. So also this FCDIR is some in this directory, and there is NWP result for 1 month result in this directory. Is also run directory is so you don't need to change these things. So it means run directory means kind of some working place to run this program, and export date domain 1 means is domain or first domain, and the forecast range 1 is 24 hour, and the forecast range 2 and 12 hour. It's like a little curious things, and they consider 12-hour forecast as true, and the 24-hour forecast as NWP forecast. So, but then from the paper, NMC master of the paper, it makes sense. So we use even Math Office and any other forecast center, and use these kind of method. But then because we don't know the truth of atmosphere, if we can find the true three-dimensional field for the atmosphere, we have to calculate those fields to a 12-hour forecast. Yeah, instead of 12-hour forecast, right?
Do we need to update our background error?
How many update? What mean?
Do we need to update the background error? I mean, every 6 months, or just like we make like seasonal background error, then you use it every time you need it?
I recommend when I started launching our Korea work model very many years ago. At that time, and we applied only one background error covariance. Calculate background error covariance matrix from the 1 year old data, NWP result. But after that, and we got a lot of problem. But then we consider those kind of problem from some data simulation framework and our observation data. But then I thought, if we can make the seasonal background error, like winter time background error and summertime background error, spring background error. So at that time, I applied those kind of strategies to our K-work model, and so after that, I can get the more better results, right? So if you can available to use computing resource or kind of strategy and kind of things, and I recommend you apply and for your season. But in the background error structure is very different, very dependent on your season.
Or do we need to also update the seasonal background error? Or just if we already created one for seasonal, we can use it as long as possible?
You already calculate your background error covariance matrix?
I mean, if we already calculate the seasonal background error, do we need to update it? I mean, every 5 years or every 10 years?
I recommend every year.
Every year to
currently
update.
Our climate is very,
Okay.
Climate has a lot of variability. So because of that, I think every year we have to change the background data structure.
Okay, thank you.
Okay, so also any other 중요한 부분은 그냥 한국말로 얘기해 주면 돼. So you don't need to any other modification. So you can just keep original default option to calculate this background error covariance, and then what is the next step? It's very easy work, right? But then it usually take a lot of time. It uses a lot of computing. You can put this coin shell, and it will make the background error covariance matrix, right? But then there are several steps. In the first, calculate difference. Could you show the step? 맨 처음에 디퍼런스 만들고 뭐 계산하고 호라이전탈 스케일 계산하고. Okay. This wrapper has this wrapper inside that kind of those coin shell script has this kind of calculation, this kind of sequential procedure to calculate the background error statistics. First is calculate ensemble perturbation from the model forecast. Means it makes some difference pi from the 24-hour and minus 12-hour. From those kind of things, you can get some difference. We can consider the difference as perturbation. From those kind of perturbation, and you can move forward to step one, stage one. Stage one is you remove area mean. So from this kind of procedure, you can calculate the kind of perturbation, and then stage two, calculate the regression coefficient, and then the 2A is usually background error use a control variable. Control variable not our original meteorological variable. We change it to dependent variable to independent variable. So psi, chi, last t, b kind of new variable from that variable and calculate horizontal covariance. So, and then stage 5 is calculate the vertical EOF covariance, and you can make the background error covariance matrix, right? So this process in calculation of background matrix is a little complicated, but end of this field you can get some background error covariance matrix file, and you can draw that file from I think they provide some kind of script to draw the background error structure. So from that kind of script, and you can see some summary your LMS structure kind of things. But then usually, for example, our Korea Peninsula, in the summertime, most of LMS comes from the southern part, and so a very high system. So we can see that those kind of error structure is very high, and those kind of things. But in 아까 요게 안 보여서 제가 전화드렸는데 and also in the winter time, and our floor comes from northwest part, and so their height is very low, so we can see those kind of things. So from those kind of investigation, and you can find your unique structure for your NWP error for your country. So this background error covariance calculation of background error covariance matrix very easy, but problem is when you enter those wrapper script. Wrapper script means there are all stages inside one console script, but it will take a lot of time, right? So usually we use case, and maybe how many days you run, maybe how long? 며칠이지? 428 hours. 428 hours, and still running. Okay, so it will take a lot of time. But in one time you make, and you can use those background error covariance matrix for your case. But in the current, so you told me you already assimilate your some conventional data for your OFDA. In this time, and your background error, what is your background error covariance matrix? From the
we're still using the default one. The
default one.
Yeah, CF3, CP3, I think.
CP3.
Yeah. I think it's there in the WearFDA folder.
Mm-hmm. Is there any problem when you use default error covariance matrix? No problem?
No, until now, no problem. But okay. I think I need to improve. We need to improve the accuracy of our forecast.
Yeah, right. Background error covariance structure means is background error covariance matrix. So like those kind of things. So when you put some one observation point data to your domain for your model, so that information of observation data and come through the flow through the NWP error covariance matrix, NWP error. It means in your domain, in the Indonesia domain, And if you learn the warp model as a cold start, with cold start, and you can get some special error structure for your domain and for your countries, your areas airflow. So from those kind of information, you have, if you are your radar data or your conventional data or radio zone data, all that kind of information through follow the those kind of error structure and spread their information to error field. Finally, you can get a good analysis, right? But in default one, and maybe they made the background data covariance matrix for default file, and maybe many years ago they made. It is kind of some. It is proposed to test some the software, DA testing. So because of that, so it's not considered for any country and each domain kind of thing. So if you change those kind of background data covariance matrix from this kind of procedure, and you can make your own and background data covariance, and then you can get more better results for your application.
Dr. Han?
Yeah, okay.
Hello? Yeah, I have a question.
Okay.
When we make the background error, if we fail to save the WARF output, or we miss the WARF output in the middle of the month, can we still make the background error?
있잖아, 한 달 중간에 빠져도 되잖아. Yeah, so no problem, right? So from my experience, no problem.
Yeah, for example, in your case, you save the WARF output from July 1st until August 1st. Is it correct? Yeah, in your case. So when in the middle of the July, we lost the WARF output.
We missed it. You don't have any results for only one date, right?
Yes.
So if so, and it's possible, but then problem is when you want to make the more good background data covariance metric, it's based on a statistic. Statistics means need a lot of data, right?
Yes.
So because of that, and I recommend 1 month data. But in this software architecture, and if you miss a lot of data inside the month data, and you can calculate background data covariance, but I cannot guarantee the performance, right?
Okay.
So maybe if you're possible, and you can put more data 1 month, but then I recommend if you want to make for 1 month more than 1 month data, I think kind of some representative data for one unique, one special season, right?
Yes.
So our Korea financial case is summertime is very unique, very hot weather, and the system is very unstable convection system like this. But in the winter time, we don't have any convection, very shallow water, shallow convection, and light rain, light snow, those kind of things. So very much different. So because of that, and the first time when I applied this background error matrix to our K-WOP model, so we just 1 year data, and the next we just put the 4 season, and the spring, summer, autumn, winter. But final stage, but then we don't have any resource to calculate every year. Because of that, and first the year, so we just apply the summertime and winter time. But in all 1 year result and similar to our 4 season background error covariance. But because our spring and autumn case is not much special and not much unique. So summer and the winter time background structure is dominant for our domain because of that. So just only 2 months, 2 seasonal background data covariance is enough. But then you have to find those kind of things. But in, yeah, right? You understand?
Yes, yes. Thank you,
Okay.
Dr.
Okay, okay. So you have any question? 뭐 설명해야 되지?
방금 미싱 데이터 있었던 거 디폴트 옵션을
Oh, okay. So if you miss some NWP result to calculate, when you calculate background data covariance metric, and so you can put this option, export, allow missing date is set to true if you want to GenB to attempt to continue with the gap in data, missing date, right?
Okay.
You can use this option. Can you see?
Yes, okay. Thank you.
Okay. 또 보여줘야 될 거 뭐 있나? 백그라운드 스트럭처를 그림 그려놓은 건 없지.
만들어진 거.
오케이. 옛날에 내가 그린 거 있긴 한데 됐다 그냥.
Mr. Choi, can you show us the data input for generating the error background?
The input data, NWP result data?
Yeah, the
right.
WORF input data, the NC
input
format
data.
data.
KD. Directory name is some KD output, KD source. 아니야. 아까 스크립트에 있다 보니까. 워프 아웃풋이 있는데. 아까 보면 거기에 보면 어떤 인풋이 들어갔는지 보여달라는. KD result. Yeah, so I learned this model for 1 month. So yeah, could you see? Can you see?
Yes.
Yeah, just this is one date, one case data, and just 3 file, and the 00 and 12-hour forecast and the 24-hour forecast. So can you go up to a higher level?
So we only need to run the model 24-hour forecasting, right?
Right. Just 24-hour forecast, 3 file. It means you have to put the history interval just 12-hour, right?
Yeah.
You know that? And so in a lamest input and all right?
Yeah.
So this is just the directory name. And in this time, I just only learned 2 times a day. For example, but if you but you already has 4 times a day result, right?
No. We just use the 2 times a day.
2 times a day. So, but if you each directory name like this, okay, inside this directory, one more time. So, and you can see the 3 file, right?
Okay. Yeah.
Yeah. If you have this kind of things, and you can put this model directory to that script, conshell script in GenB wrapper conshell script, and you can put those name to then, and you can put the script. So maybe he will provide the script configuration script, this script to you. Okay.
Okay.
Okay. So
maybe you can attach at the LMS system, right?
Right. LMS. So So I transfer. I give this script, and so his code for observation decoding to Diana, and Diana will send those files to Nina, right?
Yes.
And Nina will upload in your LMS system.
Yeah. Thank you.
Yeah. So from this kind of things, so you have to change this part, right? In the saving directory for saving a work model, right? FCDIR. You change these things, and you can try this script in your server. Okay.
Okay.
Yeah, background error covariance much important than others. So lastly, ECMWF calculate their own. ECMWF and Metapis calculate their own background error covariance. But when you improve, when you want to improve your system, in the back calculation of background error covariance is very essential and very important issue. And then you have to do some bias correction for your observation, the quality control. But then the work of quality control is very, it will take a lot of time. So sometimes your observation instruments change. Sometimes when you find some error and when you find some quality in your observation instrument, and sometimes like remote sensing observation, like a weather radar, maybe if you use weather radar data for a long time, so generation electromagnetic wave part is very waste, and so power is very much different from the older one. So because of that, then you always doing quality control for data simulation.
Dr. An, let's say if we change some parameter or update or add some, like say, let's say the satellite data. Do we need also update the background error? I mean, if we change the cumulus from the Canfritz to other setting, do we need also update the background error?
No. Background error is from the cold start data, right? Yeah. Not a data simulation model output. But then if you want to calculate the background error covariance matrix, you have to run warp model without warp DA. Okay?
Okay.
Just only run warp model with GFS, in your case, and GFS data. So not use any data simulation.
Okay. What if I change something in the parameterization section? Do we need also update the background error?
Right. If you change the physical parameterization in a model, background means NWP. Background error means NWP error. But if you change the physical process or some dynamics or some kind of option in a work model, and but in some smaller, not major option, but I think it's not changing background error structure. But then if you change the physical process or some another dynamic field, so your background error structure, maybe NWP error structure will be changed. So because of that, when you have those kind of case, so you have to change your background error covariance metric. You have to recalculate.
Okay, so it is very important to make our background error after all the systems stable.
Right.
Okay, thank you.
Okay, so is there any question? For this session for your second request for improvement of your WOP DA. Important thing is background error covariance. Second, bias correction. If your observation has some bias, like always, this observation data is compared to some truth or compared to the background, always have some kind of fixed gap, like more than 2 times higher than model observation, model result, and 2 degree, more than 2 degrees Celsius like that. Though if you find those kind of bias, you have to eliminate those kind of bias. It's very important for variational data simulation.
So it's not the bias for the post-processing, right?
Right. So if you but then I heard you don't have any verification system. But if you have verification system, you can quickly find those kind of variation, those kind of bias. Also, but then if you use a satellite data, not now, but then you told me and you plan to simulate satellite data. But in satellite data has in satellite data, and they has their own bias value. So from those bias value, we can apply the variational bias correction. So satellite data has a lot of grid point data. Each grid point has their own bias. Because of that, and from compared to this bias to the model data and some simple variational method can eliminate all bias. So it's very important key factor to improve your results from the WRF-DA. But each country and ECMWF and the MetaPIS use those kind of technique. But in when I learned the WRF-DA 10 years ago, so I didn't know that. So I just put the all satellite data to WRF-DA, but I finally got the not good result. So I didn't know that. But in a variational bias correction for satellite is much important. Also, key factor is also one key factor is background covariance. So two kind of things is very important for your WRF-DA system. Okay.
Okay.
Yeah. Any questions? So we will finalize our today's session, and so tomorrow some another he is director in our ocean modeling part, and he will explain the ocean model and some coupling model, and the result from the coupling model, and so how can we get the improvement of atmospheric result from this kind of those coupling technique. So tomorrow session, and he will cover all day. Okay.
Okay, sir.
Okay.
Okay. So thank you for your concentration. So also, and this Thursday, and so I'll give the final session. I will show you our operational NWP system, and also I provide some script. But when you ask to get some operational script, share script, right? So also I'll explain those kind of things, our displaying system and the visualization system. Also, we will make the final level. So for our next plan, so how to make some kind of, how to keep this kind of technical cooperation for the future. And yeah, how to exchange it. So also model data. Also one other things I have to explain that some another global model like our key model. So how to learn work model with a new global model. So I'll explain those issues. Okay.
Okay.
Okay. Okay. Thank you for your concentration. Thank you.
Thank you. Thank you very much.
Thank you
Okay,
very
yeah.
much, Dr.
Thank you. Thank you.
Mr. Choi. Thank you very much.
Thank you.